Oh, so today we're going to go ahead and review Chapter 5 in Designing Social Inquiry, a chapter which looks at issues regarding measurement and issues regarding research design and sort of an ends of what not to do in these areas, especially in small and qualitative research. But I'm also going to use this chapter as sort of a launching pad for our quantitative section, which takes up the majority of this class, by reviewing some general concepts and ideas that I think will give you a greater insight into what Chapter 5 was talking about, but also serve as a launching pad to get us into the quantitative research portion of the class. So the first thing we're going to look at is actually types of measurement and different types of measurement. So we need to know that largely in quantitative social science and also qualitative social science, there exists three general types of measurement, that being nominal measures, ordinal measures, and interval measures. And these measures all measure different concepts. So nominal variables are categorizing variables, in which you simply categorize yourself into one thing or another. An example of a nominal variable would be religion, or what religious affiliation are you? Catholic, Protestant, Muslim, Jewish. That's a nominal variable. Another way to think of nominal variables is a naming variable. It names something, and it's not a quantity which we can differentiate. If someone is Catholic, they're by definition usually not Muslim, and someone who is Muslim is not Catholic. But all of them are different religions. It's a categorizing variable that simply names itself. This differentiates from ordinal variables. Ordinal variables are also categories, but they're ordered in some fashion by which you can talk about size or quantity, that is less to more. The important distinction here is that the distance between those categories itself is not quantifiable. So an example would be a question about support of abortion, ranging from I support abortion in all circumstances to I support abortion before the third trimester to I support abortion in need of health and safety of the mother or child, and last, I never support abortion. So you can see how that categorization is measuring less support for abortion, but the difference between those categories, while it is reducing, that difference itself is not quantifiable, or it isn't quantifiable in a sense in which it's meaningful. So while it's ordered, the difference between the categories can be very different. So nominal is just naming, but ordinal variables are categorized, but that categorization is ordered in some meaningful fashion. When we move to interval level variables, those are what I generally refer to in my head as continuous variables. That is, they have a wide range, and the differences between each quantity that you're measuring is meaningful. The easiest way to think of this is income. Income can range from 0 to Jeff Bezos. But the differences in between are very meaningful. So an individual who makes $31,000 a year as compared to an individual who makes $32,000 a year, the difference between what they make in a year is $1,000. So the difference between those data points is meaningful. There is actually a quantifiable thing that we can identify there, which differentiates it from ordinal data. Now, to tie it back to qualitative research in some sense, although this is also a big piece of advice for quantitative research, you want to make sure that the way you measure something, the way that you record that data is in reference to your theory regarding said data. And you need to worry about this because you have to be aware of how you group things. So let's take that income variable, for example. Let's say instead of measuring income in terms of dollars, we decided to collapse it down in some way. Let's say instead of a wide range of data, we decided to make 4 categories. That is, individuals who make under $25,000, individuals who make $26,000 to $50,000, individuals who make $50,000 to $100,000, and individuals who make over $100,000 a year. So we've taken this rich variation and binned it down, binning meaning putting it in categories, into categories that are, by their definition, ordinal. They are ordered, less income to more income. But if we look at just the less income and more income category, less income includes $0 to $25,000. That's a significant difference in terms of what that individual can do. Similarly, if we look at $100,000 a year in terms of income versus what Jeff Bezos gets in a year in income, or any one of the uber wealthy, the comparison between them is an individual who makes $100,000 doesn't have any share of the resources that those who are individuals who are uber wealthy do, and thus it makes very little sense to actually compress all of that rich variation into a tinier category. That grouping error will bias estimates if you include it in a model. It will dumb down your modeling in a sense. And we never, when we're looking at quantities, when we're attempting to assess variance, when we're attempting to predict variance, which is what social science does, attempt to predict variance, we never want to use a measure or a variable that by its very nature reduces the variance that actually exists in reality. Because those variables are less exacting, less precise, and lead to less causal inference in that regard. Now we're going to run through and sort of look at these variables in Stata using NES to give you sort of an idea of what a nominal variable looks like, what an ordinal variable looks like, and what an interval variable looks like. So the first variable we have here is race. And as you can see, the categories are white non-Hispanic, black non-Hispanic, Asian, Native Hawaiian or other Pacific Islander, Native American or Alaskan, Hispanic or other Hispanic, including multiple races. So this is certainly not exhaustive, but these categories they don't measure race. They identify race. So they're naming. This is a nominal variable. So an individual who is white, non-Hispanic simply can't be any of these other categories. So this is it's a useful way to identify things, to name things, but it doesn't measure race. It identifies race. And measure sort of gets to the idea that there exists some systematic differences. And while there are differences in terms of naming, it's not measuring a concept as much as it's identifying categories within a concept. Second, ordinal variable. So this variable measures beliefs of the American public on children who come here illegally, or children who were brought here illegally, probably talking about dreamers. And this variable is measured in 6 categories, ranging from these children should be sent back in a great deal. They favor that position a great deal. Individuals who only favor being sent back a moderate, individuals who favor being sent back a little, and all the way should be allowed to say favor a great deal. And so you can see that this is obviously support for dreamers, ranging from measured as 1, very little, to measured as 6, a lot. But the difference between these things that you should be able to see is not very precise. Mainly, I think about categories, I think we should be able to identify very clearly that there exists a wide range of difference between category 1 and category 6. Should be sent back, favor a great deal, should be allowed to say favor a great deal. There's going to be a wide difference between those two positions. But look at positions 3 and 4. Should be sent back, favor a little, should be allowed to stay, favor a little. I'm not sure what the differences between the individuals in those two categories would be. They've identified themselves as being different, but I'm not sure how meaningful that difference is. And so this is what one of the qualities of an ordered variable or an ordinal variable is, that it has difference between the categories, but that difference may or may not be meaningful, or meaningful in a quantitative sense. We can order it. We can't quantify the differences between it. Lastly, we have an interval level variable. In this case, I used a feeling thermometer for support of the police. And this variable, as you can see, from min to max ranges from 0 to 100. 100 being individual 100 has a very high thermometer rating for the police. So the feeling thermometer measure ranges from 0 to 100. Think of it as like temperature, feeling thermometer. So 100, you're pretty hot. 0, you're pretty cold. And this is individuals' own assessment of how they feel about something, in this case, the police. And as you can see here, the mean is 75.4, and that's actually meaningful. So an individual who says that they are, my feeling thermometer towards the police is 78, and someone else responds, well, my feeling thermometer towards the police is 80. That's a 2-degree difference. We actually, that's meaningful. In some sense. There are problems with feeling thermometer variables, and we'll definitely talk about them in this class, but we know that there exists, at least underlying the idea of the variable, meaningful differences between each identification. And that's what makes it an interval variable, because the interval between measures is meaningful. I'm going to switch degrees and talk a little bit about measurement error. So huge block of text, but I'm going to break it down in some detail. So because there are different types of measurement error that we're going to talk about within this section, I kind of want to go through it so you can see them in reference. So the first type we're going to deal with is systematic error in measurement. Systematic error is error that is introduced almost usually by the researcher themselves, and it's introduced in a way that the recording of the data is flawed, but it's flawed consistently throughout, which means that it's problematic. It means that you're not accurately measuring the concept, but you're accurately recording it consistently. So let's say, for example, temperature. Think of a thermometer as a pretty good example of systematic measurement error. Let's say you have a thermometer that is consistently, let's say meat thermometer, because this is less problematic. Let's say you have a meat thermometer that is consistently 10 degrees low. Well, every time you measure something, it's going to be 10 degrees off, which means that you're not going to get an accurate measure of the temperature. But if you measured a number of things and it came up at different temperatures, you would know that the device you were using was consistent. And because it's consistent, it won't bias our causal inference. It's problematic in that it's not an accurate measurement of a concept. But if you're attempting to predict what causes variance in meat temperatures, well, there still exists that variance in the meat temperature. So it's not going to bias our causal inference. But it is problematic in that we're not accurately measuring the concept. But systematic error, not all that bad. Random measurement error, however, is problematic, is significantly problematic. So random measurement error in the dependent variable, that being the variable that we're trying to predict, produces estimates of causal effects that are less efficient and more uncertain. So let's say that, we'll use the meat thermometer example again. Let's say that the meat thermometer is perfectly accurate, perfectly fine, but we make an error in recording the temperatures, but we don't do it systematically. Let's say we got distracted on a couple of entries and we moved a decimal point. That's going to significantly bias any sort of results we have because our dependent variable is not measured accurately or consistently, because it provides more uncertainty in the accuracy of our measurement. So that random measurement error in the dependent variable will sort of mute any causal effects because the dependent variable itself, that what we're trying to predict, the quantity we're trying to predict is inaccurate or is measured inaccurately. When we have random measurement error in the independent variable, that is the variables it's trying to predict, this will bias causal effects towards zero. So let's say we assume that A causes B. B, temperatures in meat. We're just going to keep running with this example. And we assume that that is compared to, let's say we're taking measures of things coming out of our freezer. Well, let's say we take everything out of the freezer and set it down. Say we have 10 objects, and at random we take their temperature. Well, the last thing that we take the temperature of is going to have warmed versus the first thing we take the temperature of. That's not going to be a measure of accuracy of our freezer. It's going to be a measure of how long that meat sat on the counter. Well, that randomness in our independent variable is going to bias our assumption of causal effect towards zero. Now, in quantitative research, large N research, when we have random measurement error in the independent variable, it's a problem. When we have random measurement error in the dependent variable, it's a problem. But with large enough data, those problems get absorbed into control variables or their modeling techniques or any sort of thing. They're not as much of a problem unless they're widely prevalent. But when you're dealing with a small N design, either type of measurement error can basically create a circumstance where you aren't going to have any causal inference because your measures are simply not measuring the concepts which you want them to measure. Think about random measurement error in the NES. So in the NES has around 4,500 respondents. There is probably random measurement error in there. In fact, I'm certain some variables have random measurement error. That's going to be an issue, but with 4,500 respondents, random measurement error is going to get washed away in terms of the number of data points that you have. Let's say you have 10 data points, small N research. Let's say you only have 2 issues with random measurement error on a variable. That's 20% of your data that's inaccurate. That's a huge issue in small N research. So in small N research, you have to be much more conscious of how you're measuring things and the consistency in which you measure things. Because errors in terms of measurement are much more problematic in small N research than large N research. Another thing that has to deal with types of measurement issues is emitted variable bias. So emitted variable bias is a circumstance by which a variable that has an effect on the outcome is not included in the study. So how can we express this? Well, the expected value of B1, that is variable 1, the expected value of variable 1 is equal to variable 1 plus the effect of variable 2. So what you can see here is if we admit B2, we don't actually include it in our model, then variable 1, B1, will actually get all of the predictive power of B2, inflating the expected value of B1 inaccurately. So omitting a variable can cause us to identify stronger causal relationships that actually exist. The only times by which you should omit a variable are as if f or B2 is equal to 0. So if the effect of variable 2 is equal to 0, or the variable itself is 0, then we can omit it. But if either of those have some sort of expected function on the outcome, we need to be very careful about omitting those variables because it'll cause us because we're not measuring it, to identify stronger relationships than actually exist within our data. So this admitted variable bias is a significant problem in social science, where we draw up a hypothesis, we have a theory that informs us that that X causes Y, we collect data, we assess this relationship, and we do determine that X causes Y. But let's say we have an omitted variable. We'll call it Z. So that X has an independent effect on Y, and Z also has an independent effect on Y. Well, by not including Z in that study, we've identified a much stronger relationship between X and Y than actually exists. And so this admitted variable bias is something to think about when you're actually making modeling choices, not just in qualitative research, but also in quantitative research. So I want to go through some variables to sort of motivate this idea and show you what this looks like. So I'm including two variables on the screen so you can look at. So the first is one of the things I told you all not to do, which is binning a variable that's continuous. But I'm doing for a purpose here so that I can explain, at least in part, how regression works. So good news, you're getting an introduction to literally the last thing we're doing in class in the third week. And so this should give you some intuitive advancement when we get to the section on regression. So we have this variable on age. It's been together usually in 10-year increments. But as you can see, 70 plus is a big catch-all category. So individuals from 70 to 100 and let's say 5 can be in that category, whereas each of them have tens. And the reason why they were bin this way is you can see that in terms of frequency, that's the amount of individuals who appear in the data with that quality. They're pretty even as spread out throughout the data set. So we have age, and then we have a feeling thermometer toward President Trump. You can see it has a mean of 42. We'll explain standard deviation at a later date, but you can see there's a degree of variance in there as well. So let's assume that age has an effect on whether you approve or disapprove of President Trump. Let's say that hypothesis says that individuals who are more elderly are more likely to approve of President Trump than individuals whom are younger. Let's see what that would look like. So in this context, we're doing a regression predicting our dependent variable, that is feelings towards President Trump, measured 0 to 100 on age. And as you can see here, the age variable is significant. The way that you can tell that the age variable is statistically significant is if you look at T. If T is greater than 1.96, that variable is significant. In this context, that is 7.22, which is much greater than 1.96. And so we would identify that as a statistically significant variable. So as your age increases in those bins, you're more likely to support President Trump. That meets with our hypothesis that as you get older, the support for President Trump is likely to increase. So what does this variable actually tell us? Look at the coefficient, so COEF. Age is 2.5. We'll just put it there, 2.5. So that what that means is every step you go up that ordinal variable, the support for Donald Trump increases by 2.5 points. So that's a significant increase when you consider a 6-range category. That's over 12 points of support. So it would seem to be a strong indicator that our hypothesis was correct. But what happens if we omitted a variable here? And I'll tell you, since I cooked the books on this one, we really omitted a variable. Well, what variable is it possible that we omitted? Ideological self-placement. That is asking the individual whether you're liberal or conservative, and even more so on a 7 scale, whether you would identify as an extreme liberal, a slight liberal, a moderate, a slight conservative, a conservative, or an extreme conservative. Now, there's a possibility here that this variable will have a much stronger effect on predicting our outcome to support for President Trump than the age variable did. Well, good news with regression, you can actually assess that. You include both variables in the model, and it assesses the independent effect of both variables. So did we omit a variable? The answer is we absolutely did. Take a look at the age variable, and mainly the t-value. Remember what I said, that if the t-value is greater than 1.96, that is a statistically significant variable. Here the t-value is 1.88. That's not a statistically significant variable. It turns out that all of that causal inference, all of that evidence that we had in the last model is washed out because we omitted a variable, and that variable being this liberal conservative measure. Remember, it's a 7-point scale, ranges from extremely liberal to extremely conservative. Well, as you go up that scale, each step, so extremely liberal to liberal, the average difference in terms of approval of Trump is 13 points. That's huge. And so you can see how that variable has a significant effect on the outcome, on approval for President Trump, whereas age, not so much. So even if we disregard the fact that the variable is not statistically significant, look at the difference between the effect. In the previous model, just assessing the effect of age on approval for President Trump, the coefficient was 2.5. By including one other variable in this model, that coefficient is dropped to 0.5. So the predictive power, it is reduced monumentally. And so this is an example of what happens, what could happen, not what always happens, but what could happen when you omit a variable from an analysis. There's another other side to this coin, and that's what will happen when you include irrelevant variables in your analysis. So if the variable itself does not have an effect on the outcome, but it does correlate with one of the other explanatory variables, it will bias the causal estimates downward. So if you have two variables, or say if you have variable X and Y predicting outcome Z, and you find evidence that X has an effect on outcome Z, but Y does not. But Y and X themselves are correlated. Well, then you're going to be absorbing some of the variance in X with variable Y, and it will actually cause us to underestimate the causal effect of X on Z. Just by including Y in the model, we're muting the effect of X. Let's take a look at what this looks like. So I added one more variable to this model. Does the individual have kids or not? So we still have this age measured in 6 categories. We have liberal, conservative, measured across its 7 categories. And we have a dichotomous variable. It's a variable that can take the values of 0 or 1, 2 values. Does the respondent have kids or not? So using our 1.96 rule on T-scores, we can see that kids, 2.4 is above 1.96 and therefore has a statistically significant effect on the outcome. Liberal or conservative, 41 points is above 1.96. And in age, 1.04. No effect on the outcome whatsoever. Not even close. But is there reason to believe that age and kids are strongly related? I would think so. Remember that first category in age, 18 to 29. Is it less likely for individuals to have kids in that age group? Yeah. Individuals who are 70, what is the likelihood that they have had children? Pretty high. And so this kids variable and the age variable are likely related, which would make age an irrelevant variable that we included in the model. So let's see what happens when we take age out. Remember that the variable for kids is 2.7. So if you have kids, you're 2.7 points higher support of Trump. Let's see what happens when we take age out of that model. We've gone from 2.7 to 3.3. So by including this irrelevant variable of age, we actually reduced our estimate of the effect of kids on support for President Trump. You can see by simply including a variable in the model that was irrelevant to the outcome, that it biased our estimates of this other variable in the model. So not only do we have to be careful to accidentally omit variables from the model that should be in the model, we have to be careful to not include in the model variables that are clearly irrelevant. Now, let's take all of this back to qualitative research. In this case, we're dealing with 3,515 cases. That's really number of observations there. Let's say we're dealing with 8. We're doing small n research. If we include an accidentally omitted, or we exclude a variable that should be included, then we're going to affect our assessment of the causal effect positively. So if we assume that X causes Z, well, we're getting by not including Y, we're saying that X has a much stronger effect on Z. That's what omitted variable bias is. But let's say we include not only X and Y, but also A. And A doesn't need to be there. Well, then we're going to affect the outcome even more because we're going to actually not be able to assess how strong the effect of the variables are. So all of these warnings exist within large N research, but the problems are magnified when you're dealing with a smaller number of cases, which is all of this is to say, despite the fact that I'm a large N quantitative research, doing good small N qualitative research in many ways is actually harder than doing large N quantitative research in most cases. Because all of the problems that exist within large N research are usually magnified. Omitted variable bias, irrelevant variable, measurement error, all of these things are magnified in small N research. Last thing we're going to cover on this in this section is endogeneity. So endogeneity is a problem that exists in quantitative research, but again, it's magnified in small N research. So endogeneity describes a situation in which it's very difficult to assess which way the causal arrow goes. Meaning that you assume that X causes Y, but it may be the fact that Y causes X. And because of your modeling choices or because of how you observed something, it's very difficult to disentangle that relationship. Think of our previous example of liberal. We know how strong liberal conservative writing is in terms of predicting support for President Trump. Now, which way do we assume the causal arrow goes there? Well, we know because of a vast quantity of literature that ideology is something that is adopted very early on in individuals' lives, and that it's an identifier that it's usually very difficult to change. It usually isn't that malleable. And so we're pretty certain that ideology is a predictor of support. But we're pretty certain because of theory. We're not certain because of any circumstantial systematic control. We're certain because of previous research. Now, let's take a look for something that is very topical now, and may make you question sort of this endogeneity issue. So let's say if we were to right now take a poll, put poll in the field that assess support for police forces and simultaneously assess support for Donald Trump. Now, could you disentangle which way the causal arrow would point in that relationship? Are there some individuals in which their high support for the police would lead to high support for Donald Trump? Yeah. Are there also some individuals that because of their high support for the police would now, or for a high support for Donald Trump, would now lead to high support for the police? Yeah. And how do we disentangle that endogeneity, where we know that some individuals in our samples, their support for the police would lead to higher support for Donald Trump, and that other individuals in our examples whose support for Donald Trump would now lead to higher support for the police? How do we disentangle that? That is at core the issue with endogeneity, is attempting to assess which way those causal arrows flow. Now, in qualitative research, there are ways that you can do this. Observing your variables at different times, observing your cases at different times, observing different parts of your cases at different times, so that at the very minimum, you can set up the chronology of the circumstance. So in quantitative research, how could we assess whether those individuals that supported the police now support Donald Trump changed versus individuals who supported Trump now support the police? How could we assess that? Well, one way would be to do what we call panel surveys, which is to take the same group of people and ask them the same questions over time, and we could identify which individuals switched or which way the causal arrow points and at what time that sort of stimulus kicked off the change in that support. But endogeneity is a sticky issue. And it's one that we'll actually come back to in this class, but I just wanted to use it this time to sort of point out that this issue actually exists, and it's an issue to think through when you're designing your own research.